Ladies and gentlemen, thank you for attending my talk. My name is Robert Magnusson. I'm with the Department of Electrical Engineering at the University of Texas at Arlington, and I'm also with Resonance Sensors Incorporated. Today, I will discuss periodic thin film optical sensors, their technology and applications. I want to thank the organizing committee for inviting me. Here is the outline of my talk. I will begin with the fundamentals of the guiding mode resonance effect. This includes evanescent waves, leaky mode structure, the block mode picture, their dispersion properties, and the local electromagnetic fields that enable the sensor action. I will show some sensor response examples, fiber tip sensor embodiments, discuss fabrication and design methods. I'll discuss the multiparametric sensing capability of this sensing concept. I will brief commercial sensor technology development, show a couple of examples with COVID and Neuropeptide Y, and if we have time, I'll address some other applications that can be implemented with this methodology. So here is a summary of the basic resonant interactions that occur on periodic waveguide gratings. In fact, the fundamental resonance effect is based on the excitation of leaky eigenmodes that appear in one-dimensional or two-dimensional dielectric films. When we have a low spatial frequency grating, namely large period relative to the wavelength, an input wave scatters plane waves in multiple directions as shown here, and these integers indicate the diffraction order number. Shown here also are, in blue, are higher order diffracted waves that are evanescent. They're not propagating in the outside space. These are very critical. Now, to have an efficient interaction, namely not have these higher orders robbing energy away from the business orders, namely the zero reflected order and the zero transmitted order, we go to the sub-wavelength regime, where the period is smaller than the wavelength. This is also called the zero order diffraction regime, and it looks like this. This could also be done in two-dimensional structures as shown here. The leaky waveguide modes that are induced on these periodic structures constitute the lateral transport mechanism. The phonoresonance effect implies a continuum of input frequencies or wavelengths that address discrete states, which are modes in this case. For a thin film waveguide, where NF index here is higher than the surrounding refractive indices, then there can be a guided mode. This is used in fiber optics and in many integrated photonic devices. These modes are structured like this: the fundamental mode, the first, second, and third, and so on, TE0, 1, 2, 3. And they have these mode shapes, and they are discrete modes, and other shapes cannot exist in there. One cannot excite this by broadside illumination on this structure. One cannot excite these modes that way. So we need the periodicity as the coupling means. The coupling takes place when the evanescent waves address these discrete modes in there. Sorry about that. And we can see computed fields here. These modes, at normal incidence, these modes are counter-propagating, forming a standing wave with snapshot of the fields shown here. The workhorse effect is the lateral block mode resonance phenomenon. And here we just summarize the fact that discrete photonic lattices shown here behave similarly to connected photonic lattices noted there. So if we take what we call a zero contrast grating. There's no contrast here, and compute for typical parameters the reflectance R0 measured on this color scale as a function of the wavelength and the homogeneous waveguide thickness shown here, DH, at DH0, implying the disconnected lattice, we have a wide band there. As we increase this thickness, these wide band patches still appear, even the widest one is maybe here, 400 nanometers. So one sees that there's a continuity in physical behavior between the discrete and the connected lattice. So because there is some disagreement in the literature about the physics of this effect, namely some people say it's due to Fabry-Perot local modes here, or me resonance in these discrete particles. There is some disagreement in the literature about that. And we've been actually writing papers about that, trying to clear that up. So so in summary, the simplest case is the one-dimensional structure, the leaky eigenmodes that occur in 1D designs. And the good thing about 1D sensors is that we can support this discrete TE and TM resonant modes if unpolarized light is incident upon the device. So so that gives polarization diversity with basically for free. So in summary, the sensor resonance reflection is driven by excitation and re-radiation of these lateral block modes, driven by these evanescent diffraction orders. So basically the reflectance is a diffractive effect and not related to any discrete interfaces here. So the local Fabry-Perot or me modes are not the enabling effects. I repeated myself a little bit there. Proving this further, we take a pulse for a grid shown here, and as the pulse is fired upon the grid, clearly there is a lateral propagation, which is what we contend is a fundamental effect. And here are some of the parameters of this particular membrane grid that we are modeling here. So it's possible to understand some of these effects based on the leaky stop band dispersion diagram. So again, taking a resonance sensor here, periodic, having an input light, reflected light, and transmitted light with evanescent diffraction orders driving the case, the second stop band or leaky stop band has this characteristic. This is essentially frequency, and this is wave number. And each mode that is supported has a different resonance frequency here and here, and a different, and they have their own band properties shown schematically here. This is not computed, this is just schematic. Now, so there is one leaky edge per mode. This is the leaky edge. That's where the light creates a reflection resonance, and one non-leaky edge per mode, as shown here for this symmetric structure. So nowadays, the non-leaky edge is called bound state in the continuum, or BIC. If we were to just tilt the structure slightly and break the symmetry, we would have a resonance peak there as well. So in 1998, we actually showed how this works, and basically you can call it an experimental verification of the dispersion diagram, because this is wavelength and this is incident angle, which represents the lateral wave number. And this was a world record experiment with very high efficiency, 98%, about 2 nanometer full width half max there. And as at normal incidence, we just see one peak, because the symmetry protected BIC edge is not resonant, as you see here in this computed diagram. And as we angle, then it comes out, and now we have these two peaks that really agree. This experimental data agrees with this blue dispersion diagram here. So the leaky mode field pattern is very important. We can have very high Q local fields or medium level Q local fields. Here is a schematic diagram of just a structure used for calculation. And with an input wave of unit amplitude, you can then at resonance that zero order is completely reflected and interferes in space and produces this magnitude 2 there. You can see that standing wave there, and that standing wave is also shown here, and this is the device. And we have a field decomposition in the periodic structure given by this coupled wave expression here. The field is represented by these S values, which are the amplitudes of the inhomogeneous plane waves representing the space harmonics, where I means the order number, I1, 0, 1, 2, 3, or -1, -2, and so on. So at normal incidence, S1 and S-1 represented by this curve are counter-propagating and forming a standing wave shown here. And you can see the evanescent tails hanging out, and this evanescent tail on either side is useful for sensing because that's what interacts with the biolayers. So here's an example of a guided mode resonance sensor where originally we drew this as an optical fiber. This could just be a substrate, input light and reflected light and transmitted light here. So the periodic dark patches imply this sensor structure, and the gray region here represents the bioreaction, which includes a chemical link layer that locks the antibody down on the sensor surface to receive the antigen. We're interested in measuring, in this case, the antigen-antibody reaction, but a variety of other types of chemical lock and key experiments can be made. So one important point about this sensor is that it is label-free, which means we are not using any absorbent, radiating, or fluorescent tags, which are molecules that provide an optical signal when the bioreaction takes place. We don't use that in this technology. So for a typical sensor, the data shown here, period 530, fill factor half, 50-50 duty cycle, few hundred nanometer thickness, and so on. We compute the response when we change the refractive index of the surrounding region of the sensor. So here are the two polarization states, the TE and the TM states. And for one refractive index, you see one response in T and another in TM, and then we change the index, and these resonance wavelength shifts. And that's the key to the measurement. So there are the lines are quite narrow, much narrower than for the surface plasma resonance sensor. That is also a good sensor, by the way. But we can have two polarization for each measurement, which can be very useful. So for this example, we measure for the biolayer attachment, we measure the peak wavelength versus the thickness of the biolayer in angstrom, assuming a refractive index for that biolayer, maybe 1.4. And we see the shift here in wavelength, and then we compute the sensitivity in nanometers in wavelength per angstrom on the scale, added material. And we get some number here like 0.02 nanometer shift for every angstrom of thickness that's added to the biolayer. Now, if we have a background refractive index measurement or sensing, then we take the peak wavelength versus refractive index of the background, and this is just for TE. And so here is the shift is pretty linear in this case. You see the wavelength changes as the refractive index changes quite linearly, and the sensitivity is pretty much constant because this is pretty much linear. Sensitivity is the shift per unit refractive index change, nanometers per REU. So this sensor has a sensitivity of about 400 nanometers per REU. And this sensitivity can be varied quite broadly depending on the sensor design and the wavelength that you use. So here's the first fiber tip resonance sensor published in this paper here in SPIE Photonics west in the year 2000, and it wasn't a very good sensor. We could just barely see the dip here, but it still worked. It was actually not quite straight cut, so we saw two peaks, and so those correspond to the split peak that happens when you angle the incident wave. And here shows the actual sensor. It's a multimode sensor, fiber tip sensor. You can see the periodic structure there, and here show the parameters of the actual device. And recently we have improved this by taking a better cut sensor and using actually a silicon nitride grating here instead of a photoresist grating. And we fabricated this in our lab. And this is actually analyzed with taking into consideration the mode profile in the fiber that is actually illuminating it. It's not exactly a plane wave, even though it's close to a plane wave when this gets very large. So here shows some SEM images of a couple of different sensors. Here shows the resonant approach, and these are the results where we basically measured. We changed the refractive index of the background water plus IPA and IPA, and we see the shift, and then we computed the response, and this one has about 200 nanometers per RVU. So the chief features of these sensors are summarized in this table. The polarization is arbitrary. Remember, for surface plasmon resonance sensors, they only work in TM polarization. The angles can be arbitrary too. The mode structure is complicated. So higher modes can provide new peaks, which is useful. The line width is between 1 and 10 nanometers, high sensitivity, good accuracy, and the efficiency can be very high. We have, as I showed you, demonstrated nearly 100%, and we actually demonstrated 100% efficiency, or 99.999. And but that's not necessary for sensors. Sensors can just use a low efficiency because the main thing is the shift in frequency, not the efficiency of the peak. So we use a variety of design methods. We solve the Maxwell's equations rigorously in a variety of ways. The particle swarm optimization method is an inverse numerical method that in which you can actually give the code your resonant wavelength, and it will find the sensor structure that produces resonance there. That's one example. We do film deposition with E-beam evaporation, sputtering, and PECVD. We do patterning fundamentally with nano imprint lithography or UV laser holographic interferometry, sometimes with E-beam. And we use SCM, AFM, ellipsometry, and spectral analysis to characterize these devices. Here shows just a picture of the lab where we work. This is the interferometer, UV 266 nanometer UV laser interferometry here, processing the etcher that we use in our lab. We have an SEM, AFM ellipsometer to measure the thin film thicknesses that we deposit, and the spectroscopy equipment here. And for nano imprint lithography, we make a master, and then we press the master down on nano composite and then peel it off, so we can have a sensor right there. Now, if this is a little bit hard to control, so sometimes we just make a surface on a substrate, and then in that case we would coat that surface with maybe in our Kurt Lesker here to have a resonant film sensor. And these prototypes can be scaled up, or are actually scaled up by injection molding and using commercial vendors to deposit either silicon nitride or titanium dioxide films for us. So here shows some laboratory data for a 500 nanometer period nano imprinted device. Here shows 96 well plate already with thin films deposited. And this is a 10 by 10 biochip with 100 micron diameter sensors. So as I said, this sensor is a multiparametric because we can use multiple resonant modes to determine all three unknowns. The unknowns are the biolayer thickness, the refractive index of the biolayer, and the refractive index of the background solution, because it can change. Sometimes you can assume it's constant, then you just have to deal with two unknowns. And there is no other sensor technology that can accomplish this with a single unpolarized beam of white light. That's a very economic. That's a very economic solution. And so we can, for example, for a single polarization state, you could use TE0, 1, and 2, or for a dual polarization, we could use TE0, TM0, and TE1 for a 3x3 matrix to solve, or to back this out with the RC rigorous coupled wave theory. Usually the most accurate is to fit the data to an electromagnetic sensor model, and here's a couple of papers that discuss this in much more detail than I have time for today. So in summary, the multiparametric sensor proceeds that there is a bioreaction that produces spectroscopic data that is can be fit in real time to the RCWA model, which runs really fast. And from that, we can, as a function of time, back out the biolayer thickness in nanometers, the biolayer refractive index or its density, the background refractive index, the background solution, and then we could convert this data to modality and surface mass density if we care to. So this technology is commercialized by Resonance Sensors Incorporated. There are many advantages listed here. The most important part is that this is mass producible. These sensors are mass producible economically and useful for a lot of important applications, including medical diagnostics, COVID, and other things. Here shows in review the input light exciting these modes. Here TE has one mode shape, the TM has a different mode shape. It depends on the local conditions. And here's the reflected narrowband light. We monitor with both of these resonant modes what's going on when there is an analyte binding to an antibody or antibody binding to an analyte. And again, the physical principle is this wavelength shift that occurs upon binding, namely changing the environment of this waveguide, which causes this shift in the resonance wavelength. And here shows the commercial system. This is the reader there. It's a label-free operation in a microarray format. It's got very efficient plate layout and plate layout control. You can have multiple experiments running simultaneously and extremely efficient reporting modality incorporated automatically there. So the 96 well plate, here's a 384 well plate, here's a 96 well plate, standard plates, and the 96 well plate scans in less than 20 seconds. So that's really rapid scanning of what's going on. So here shows an example of COVID. We can use serum, raw blood, or saliva to test for antibodies against the COVID-19 antigen. And this is very famous nowadays. It's on the news every day. Here's the cell. Here's the COVID virus, and it has S protein spikes. The spike protein is here, shown here, labeled down there. It comes onto the ACE2 receptor on the cell, and it binds there, and then when there is a viral uptake, the cell then replicates the virus and releases it. That's how the virus replicates itself and spreads. So the S protein on the virus is the key, and the ACE2 protein on the cell is the lock. So it's a lock-key interaction. And here's an example. Here's a 96 well plate in which we have put COVID-19 antigen immobilized, anchored on the top of the plate there. And then the antibodies come in and bind, and we monitor this antibody binding to this antigen there. And so here's a patient that is confirmed positive. We have some stabilization steps here, and then we add the sample at about 12 minutes, and immediately there's a resonance wavelength shift from about 50 picometers to about 350 picometers here, measured here on the scale. And so, and post-wash remains And so this is a confirmed positive test, where for a confirmed negative patient, basically essentially nothing happens. So these results, there are 4 wells dedicated to each experiment here, each patient, and these are averaged, and the reference buffer is subtracted from the data. We have 4 wells per sample, 24 tests in a single run, and 30 minutes per run, as shown here. Well, actually less than 30 minutes per run. So it's less than 2 minutes per test, which is very efficient. So another example is the neuropeptide Y binding dynamics that we measured under an Air Force contract published in this paper here with our colleagues. NPY is, or neuropeptide Y is a 36 amino acid peptide in the pancreatic polypeptide family found in large quantities in the brain and the nervous system. Affects feeding behavior, anxiety, and affects regulation of physiological function. So there's some interest in monitoring that. Here in this experiment, we sense and quantify anti-NPY binding to avidin D, and then neuropeptide Y binding to anti-NPY using a sandwich approach. And so the devil is always in the chemistry. So you have to prepare the plate, put down silane on the plate, link that to the plate, then that becomes the cross linker, and then the avidin D binds to those, and the anti-NPY binds to the avidin D, and then the NPY binds to the anti-NPY, and because the NPY is very small, we detect its presence by putting the large anti-NPY back on it like that. That's called a sandwich assay, and that produces high sensitivity detection. And so this shows the reaction here, where there's baseline and a delay, and there's NPY binding to anti-NPY, and there's sandwich NPY binding. And you can see, depending on the molarity of the NPY here, we get these wavelength shifts in some fraction of a nanometer, 0.23 nanometers or 230 picometers, shown here for the largest concentration of the NPY of 10 nanomolars. But we go down to 0.1 picomolar, we still see a shift there. So we're basically close to 1/10 of a picomolar detectivity there. So that's a very good result published in this paper there. And as far as other technology developments related to this fundamental resonance effect are concerned, we can mention a few examples. These are, and here are these basically these where what these things are and where they're published in optics letters. It's not a precise reference, unfortunately, but if you Google these titles, it will pop up. And so here's an unpolarized resonant grating reflectors with 44% fractional bandwidth. This is a single layer device as shown here. This is a 3x3 array of them. And here shows the wideband response from about 1,000 nanometers to about 1,500 nanometers with very, very high efficiency. Here shows a polarizer that we made that passes one polarization state and blocks the other, so that we can separate these polarization states, which is the essence of a polarizer. By concatenating a couple of these devices, we get an extinction ratio of about 100,000 in about a 50 nanometer bandwidth, which is a lossless measurement. And we've been interested lately in long wave, in the long wave atmospheric window between 8 and 12 microns, which is very useful for a lot of applications. And here it shows a letter. Here shows a device in the around 10 micron resonance. Actually, a wideband reflector. This is a single layer device made with germanium on zinc selenide, and it has about a couple of micron bandwidth shown there. Here shows a couple of notch filter in 2 different polarization made also in the long wave region. And we also designed and actually fabricated tunable filters where we vary the period. If the period is approximately constant locally, there is still resonance. And so by by judiciously varying the period, we can actually tune the resonance wavelength. And this shows here, this is actually a trick where we vary both the sublayer and the period. That's the best. And that shows very nice filter reflection notch filter performance across a wide bandwidth range from about 5 micron to about 14 micron. And this shows a Raman experiment where we can actually angle the device and then separate the two resonances so that a Raman shift in silicon is precisely met, so that the excitation is here and the Raman generation is at the other resonance peak. And then other data, here's a dual serial device that is polarization independent. Here is again a polarizer, single layer polarizer, very beautiful device. You can see the SCM over there. There's a couple 100 nanometer bandwidth there, separating the T and the TM states. Here's a resonant bandpass filter, single layer device, again, showing a white low sidebands and a sharp transmission peak. And here finally is a delta function resonant in angle versus wavelength. This is essentially a simultaneous spatial spectral filter that can allow spectral filtering without focusing the beam, as in the traditional aperture-based spatial filtering. So in summary, I've reviewed the physical principles and technological implementation of the guided mode resonance sensor concept. There is a variety of different architecture and materials design possibilities for this sensor type. And one can pattern in 1D or 2D dimensions. And people do both. And the application fields include medical diagnostics, as I showed, biochemical analysis, drug discovery, environmental monitoring, and many other applications. But if we allow multiple resonance peaks, then we can do multiparametric sensing. And I call the sensor the complete biosensor for that reason. I showed a couple of examples, NPY and COVID-19. So in summary, this is an economic and expeditious sensor solution. Now, connecting to thin films, its implementation does require high-quality thin films to be etched via masks or to be deposited on a periodic surface to form the resonant film. And here are the acknowledgement to our sensors and a snapshot of the group. And I thank you very much for your attention.